This is the video for the online final exam practice tests that cover electron and nuclear. This first question should be a real easy one. How many valence electrons does bromine have? So you want to refer to your periodic table. You find bromine, it is a halogen. For valence electrons, you just count left to right, skipping the transition metals because they behave a little odd and they can move their valence electrons around. And you just count over. So all of the halogens have 7 valence electrons. So that is what bromine has. Let's go to the next question. Back to this. It gives you an electron configuration. Now there's different ways you could do this. If you want to, you can add up the exponents and then compare that to the atomic number. If you don't feel like doing that and you know the periodic table method, what you can do is just look for the one that ends in 5p2. So for the periodic table method, this is the one where these first columns are the S block and it goes 1, 2, 3, 4, 5, 6, 7. The P block are these last several rows and they go 2, 3, 4, 5, 6, and we could do 7 down there. Now the part you have to remember is D is in the middle, and that goes 3, 4, 5, 6. And then you have F at the bottom, and it's 4F, and then 5F. So for this problem, it was ending in 5p2. So you could just go to where 5p2 is, and that is 10. Now if you added it all up, all those exponents, you would get 50. You could do it either way. Knowing the periodic table method, how this is set up, I think is useful though. It will make going through questions a lot easier and quicker for certain questions. The first element to have a d orbital, well, I just had it in there. This was 3d. So the first element according to this periodic table is scandium. Let's move on. All right, so now I have orbital box notation drawn out. Now again, you can add these arrows up because these are the electrons, or you can go to 3d3. Right, so if you remember the periodic table setup, 3d3 is right here. It's the third one in, so it's vanadium. Like I said, you could also add up the arrows, the same as adding up exponents, but I feel like if you know the periodic table method, it's even quicker. Now remember when you're doing orbital box notation, and it's not coming up in this example, so this 3p section here, let's say you're filling out something an atom that has 4 electrons in the 3p orbital. So what you do is put 1 in each of those orbitals before you start doubling up, right? Orbital box notation, all right, so we just did that one. According to the following electron configuration. Okay, now for this one, if it's asking you about the electron configuration, whether it's in the excited state or the ground state, the ground state just means the orbitals were filled in the order that you would expect, and that's what you want to look for. So in this one, it's going 1s2, 2s2, 3s1, so that makes sense so far, but then it jumps up to 3p1, where really it should end in 3s2. But what it's telling you is that one of these electrons jumped to a higher energy level, and that's what the excited state is. It's an electron, or at least one electron, going to a higher energy level. So I would say for that one, that is excited, and it's because this P is in there a little too early. It should go 3s2 and then move on to the P level. Type of decay. Now remember when you have a decay problem, so this is telling you that this iron 52 decays, so that's the only thing to the left of the arrow. You're getting this cobalt 52, but just like anything else, we have to make sure the masses and all that stuff add up here. So you have 52 on the top and on the left for the mass number, you have 52 on the right. So whatever this particle is, it's going to have 0 mass. Now the odd thing here is you're going from 26 to 27, which means mathematically this has to be a -1 for this to add up to 26. So that ends up being a beta particle. Beta is the odd one where we were saying a neutron in the nucleus splits apart into a proton and an electron, and the electron gets shot out of the nucleus at high energy, and that's where this beta particle is coming from. But now, since the neutron split into a proton and an electron, overall the mass didn't really change because electrons, we say, have zero mass, and the protons and neutrons are really close. But you end up having an extra proton, which is where this atomic number is going up by 1. So that's beta decay. The other type of decay we did was alpha. So if you have an alpha decay, it's telling you that one of the products is an alpha particle. You can write it different ways. You can have an alpha symbol or a helium symbol. It doesn't really matter, but it has to be 4 up top and 2 on the bottom. All right, so remember when it says decay, it's one thing to the left of the arrow. Now, bombardment means you have more than one thing to the left of the arrow. And this is asking you what isotopes, and we're going to fill in what goes here, would have to be bombarded by an alpha particle to produce phosphorus 30 and 1 neutron. Now, you still have to do the same general idea. The reactants added up have to equal the products added up. So on the product side, this adds up to 31. So you need a 27 here, because 27 plus 4 will give you 31. You have a total of 15 on the right. So you need a 13 here to give you 15. And then you find out what has atomic number 13, and that is aluminum. So you end up getting aluminum 27. The next problem is a half-life problem. Now, in this problem, I am giving you 2 lengths of time, minutes, 7.2 minutes and 2.4 minutes. So what this is telling you is that the half-life of zinc-71 is 2.4 minutes. But what happens, if you start off with 100 grams, they want to know how much is left after 7.2 minutes. So anytime I give you 2 lengths of time, take the longer length of time and divide it by the shorter length of time. And that's going to tell you how many cycles it went through, and that looks like 3. So that's 3 cycles. So now what you do is you set up your little table here. I would put initial or start or whatever here. The reason why I tell you to do that is so you don't just put like a 1 here, because that's going to put you off by a whole cycle. So you're initially starting with 100 grams. So after the first cycle, there is 50 grams left. After the second cycle, there is 25 grams left. And then after the third cycle, that gets cut in half again. You get 12.5 grams, which matches this one. I guess if you wanted to pay attention to significant digits, you could put an extra 0 in there. All right, so that is the review for the electron and nuclear.